Hello, everyone. I welcome you all to the fifth Young Scholars Exposure event organized by JBSPDF. And before I introduce our speakers to you, let me tell you the format. So it's a 20-minute talk. Each speaker will be given 20 minutes to present their talk, followed by a 5 minutes Q&A in case the audience has any questions, followed by our review by the reviewers for about 30 to 40 minutes. Before introducing our speakers, we have with us two reviewers today. Our first reviewer of the day is Dr. Debmalya Panigrahi. Dr. Panigrahi has been here with us before, and we welcome you again, sir. Dr. Panigrahi is an associate professor of computer sciences at Duke University. Before coming to Duke in 2013, he had spent a year as a postdoctoral researcher at Microsoft Research Redmond. In 2012, he obtained his PhD in theoretical computer sciences at MIT under the supervision of Professor David Carver. And before going to MIT, he worked at Bell Labs. He obtained his bachelor's and master's degrees in computer science and engineering at Jadavpur University, Kolkata in the year 2004 and IISER Bangalore in the year 2006, respectively. Dr. Panigrahi is a JB Scholar of the year 2000. We welcome you, Dr. Panigrahi. Our second reviewer, and we are delighted to have him for the first time, is Dr. Subramaniam Ananthakrishnan. Dr. Ananthakrishnan is a JB Scholar of the year 1960. He is an internationally and nationally known radio astronomer and radio scientist. Dr. Ananthakrishnan had a brilliant academic career. He got his BSc, BTech, and MTech degrees from Calcutta University, and later he did his PhD from TIFR and University of Bombay in the year 1976. He was deeply involved in the construction, commissioning, and operation of two major radio astronomy programs and facilities in India, one which is known as the Ooty Radio Telescope he commissioned it in the year 1970, and the Giant Meter Wave Radio Telescope, GMRT, in the year 1999. He was the project scientist and head of electronics and control systems of GMRT during the years 1981 to 2000, and he commissioned GMRT in 2001 and was its observatory director till the year 2004. He retired from TIFR as a senior professor in the year 2007. Since then, he has been an adjunct professor in the Electronic Science Department of Sabitri Pune University. Thank you, sir, for being here. We are very honored to have you. So without any further ado, I'll move on to the first speaker of the evening. The first speaker of today's evening is Mr. Agnibha Banerjee. The title of his talk is Exoplanet Atmospheres and the Search for Habitable Worlds. So Agnibha is a JB Scholar of the year 2016. He is a graduating B.S.M.S dual degree student from IISER Kolkata. Astrophysics, particularly the search for other Earth-like planets, has always been his topic of interest. He shall continue to pursue this as a PhD student at the Open University UK from the year February 2022. Other than academics, he loves consuming science fiction and fantasy fiction in any form and also swimming. Hi, Agnibha. We are glad to have you. You can start sharing your screen and begin whenever you're ready.
Thank you. Thanks for having me here. And hi, everyone. Good morning, evening, whatever time zone you're in. So I shall start sharing my screen now.
Yes, please share your screen.
Wait. Is the Zoom thing still visible?
Yeah. We screen.
Yeah. Okay. Is this better?
Yeah, this is okay.
Okay. So hello everyone. I'm Agnibha Banerjee, and today I'll be talking about exoplanets and the search for habitable worlds. All right, so let's get started. So first, what are exoplanets? Exoplanets are planets that do not orbit the sun. They can be orbiting other stars, or they can be just drifting freely in space, also called rogue exoplanets. The name comes from exo or outer and planets, which is just planets. So right now, this field is still in its infancy or maybe teenage, and I shall go through the basic techniques of detection and characterization of such planets. This picture is just an artistic impression of some exoplanets that have been discovered in the past. We have nowhere near these images so far. So before we get to search for habitable worlds, we must first find the planet. So I shall start with the methods of detection. Right. So so far, as of 5th August 2021, about 4,461 exoplanets have been discovered, which is a lot, considering this number was just one in 1995. In 1995, Didier Queloz and Michel Mayor discovered the first exoplanet around a sun-like star, for which they won the Nobel Prize in 2019. This plot shows a mass versus orbital period distribution for all the known exoplanets. And you can see that, and the different techniques used for monitoring and detecting them have also been plotted. So you can see from this plot that the two major techniques are radial velocity and the transit method, which we shall talk about soon. And there's other methods, and we shall also mention the fourth method, imaging, in brief. Right. So first, the radial velocity method. For the radial velocity method, there's two pieces that we need to bring together. The first is redshift. What is redshift? Redshift is the phenomenon of the wavelength of light moving towards the redder part of the spectrum when an object is moving farther from us, and towards the bluer part of the spectrum when an object is coming closer to us. This is analogous to the Doppler shift of sound, Doppler effect in sound. Like if you hear a train coming towards you, it's shriller, and if it goes away from you, the frequency decreases. So here in this illustration made by the Royal Swedish Academy, you can see that if a star is coming towards us, then the light from the star gets blue shifted. And if it goes away from us, then the light from the star gets red shifted. Now, why are we interested in this? We are interested because exoplanets are really small compared to the star and hard to spot. So what we can spot is the star, and we can spot the light from the star. So we can say that when the star is wobbling back and forth, that something is around it, maybe another star, maybe a planet. So the second piece of the puzzle is spectroscopy. So wait. So every star has its own unique stellar spectrum. This color bar plot type thing in the bottom is just a crude representation of the absorption lines present in a star spectrum. These are caused due to the elements that are present in the star's outer layers, mostly hydrogen and helium, which have some significant absorption line, which have some specific signature absorption lines in certain wavelengths. So from experiments on Earth, we know that when the object is stationary, at which wavelength these lines should be. So when a star is wobbling, the light is getting red shifted and blue shifted. We know that how far they are deviating from their original positions. And we can plot this signal as a curve, like has been shown in this plot. And as it turns out, the amplitude of this signal, which can be measured, is actually proportional to the ratio between the mass of the planet and the mass of the star. The mass of the star is a quantity that we know from stellar models, or for me, just from catalogs. And knowing the signal amplitude and knowing the mass of the star, we can, and several other constants that go in there, we can actually calculate the mass of the planet. So now we have a way to get the mass of the planet without even looking at it. So what else in a planet is important? Well, the radius. So what can we do for that? we come to the second method, the transit method. Yeah. So I just want you to take a look at this video first. So I'll speed it up. Sorry. What happens in the transit method is when a planet passes in front of a star along our line of sight, it creates a dip in the intensity of the light that is coming from the star towards us. So the size of this dip can tell us a lot about the radius of the planet. And also the width of this dip, how long the dip is, can tell us how far the planet is from the star. Now, this does have its, now this is quite straightforward, but this has its disadvantages in such that, say if the star wasn't aligned, if the orbit of the planet wasn't aligned perfectly along our line of sight, then we would have missed the transit. So transit method is not ideal for most scenarios, but anyway, it can be calculated, this transit depth that was shown in the dip in the previous video can be calculated from the transit light curve, and it can be modeled using several transit models that are available in the literature nowadays. And the transit depth gives us information about the ratio of the planet and the ratio of to the radius of the radius of the planet to the radius of the star squared. So from this, if we know the radius of the star, we can calculate the radius of the planet. So now we have the mass of the planet and we have the radius of the planet. And from the transit method, we can also get the orbital distance of the planet from the star. So in the next video, we shall show a comparison between what happens if two different planets transit the same star with different radii. So if we have two planets, one small and one big, orbiting the same star, the big one will produce a huge dip, while the small one will produce a small dip. So from this, you can say that we are kind of biased towards detecting larger planets, both in mass and radius, which is the reason why most of the planets that we have detected so far are classified as hot Jupiters, which are very large Jupiter-like planets orbiting very close to their host stars. These are not seen in our solar system. And detecting Earth-like planets is very difficult because Earth has a small radius and mass compared to Jupiter. The third method, called direct imaging, is the most straightforward of them all. It's just taking a photograph of the star with the planets going around it. This beautiful illustration is created by Jason Wang and Christian Marois. So the philosophy behind this is you just put, if you are looking at a car headlight head on, then you can't see the rest of the car properly. But if you block out the headlight with your hands, then you can see the rest of the car with the headlight blocked out. So this was taken from using the Keck Observatory, and filter was put in front of the detector to block out the region where the star would be, so that the 4 planets orbiting the star HR 8799 could be detected. And in the future, such a mission is planned, the New Worlds mission, in which 2 coordinated satellites shall be launched, one telescope and the other a star shade, which is a huge cloth type thing that will expand in space and block out the star in real time compared to the telescope, so that the planets around the star can be detected in greater detail. But this is in the far future. However, very few planets have been detected through direct imaging, to be exact 53. But as Dr. Hu would say, is 53 a lot? That, well, depends on the context. Now, detection is not everything. So far, we have learned, we have seen the methods that are used to detect exoplanets, but now we shall come to the question of whether they are habitable or not. So to check whether they are habitable or not, the first thing we can do is measure the orbital distance that they are from the star. This is a plot showing the habitable zone around different kinds of stellar classes. Stellar classes are just like stars that have different temperatures. So there is a particular region around every star in which liquid water can exist. By habitable, what we mean is habitable for Earth-like life who need liquid water. So maybe other forms of life exist who don't, but what we're looking for here is liquid water. So there's a kind of zone around every star in which liquid water can exist. And if a planet exists in that zone, we can say that it has liquid water. But wait, the story is not so simple. If we could do that, it would have been a lot easier. But why is it not? Well, there's a final piece to the puzzle, the atmospheres of exoplanets. Why are atmospheres important? In our solar system, let's take a look at an example for say Venus. Venus is very close to the Earth. It's basically a twin to the Earth. It's similar in size, similar in mass, almost similar in distance to the sun. And since it was very beautiful in the sky, detected by the ancients, they named it after the Roman goddess of love and desire. However, in reality, Venus is a lot more like this. It has a scorched surface, it has clouds of sulfuric acid, and it has a runaway greenhouse effect, so that its surface temperature is very, very high. It's above 400 degrees Celsius. It's hot enough to melt lead. But it's very similar to Earth. So what went wrong? Its atmosphere. Earth's atmosphere is life-giving, while Venus's atmosphere makes it into a hellish kind of place. So how can we look at exoplanet atmospheres? They are really thin and they're very far away from us. Well, the technique that is used is called transmission spectroscopy. Transmission spectroscopy was done is that when the planet is passing in front of the star, there's a thin ring of the atmosphere around it, the annulus. And the light that is coming through that ring is split into different wavelengths using a prism, or we get a spectrum from that light. And then if you plot that spectrum, then you can see that there are different absorptions in different wavelengths. Why is this? This is because there are certain elements and molecules in the atmosphere of the planet which have signature absorption lines. These absorption lines can be modeled using physical models, chemical models, etc., as can be seen in this right side plot here. This is a paper by David Singh from 2016, in which he modeled the atmospheres of 10 hot Jupiters. And we can see that sodium and potassium is a feature in almost most of these planets. And at 1.4 microns, there's also a water feature that can be seen in most of these planets. In more detail, this is a illustration created by Laura Kreitberg. Transmission spectroscopy is the study of light at different wavelengths. So if we look at the light coming through the planet's atmosphere at different wavelengths, the atmosphere would seem less opaque at some wavelengths and more opaque at other wavelengths. At the wavelengths where it is less opaque, the intensity will be more, and the wavelengths where it is less opaque, the intensity will be less. So that was transmission spectroscopy. And here is a more recent work on transmission spectroscopy that was done on the atmosphere of WASP-39b, another hot Jupiter, by Hannah Wickford. In this, you can see several features that have been labeled, like H2O and CO2 and sodium and potassium. But this also gives a sense of the quality of data that is available right now. This is one of the better data plots that are available. Like, at least this peak is completely like filled with data points and stuff. But this part of the spectrum has nothing, no data, because this was taken using the Hubble HST WFC3 camera, and that doesn't have a wavelength range in the infrared as we want it to. So most atmospheric characterizations that have been done so far have detected a lot of molecules, but the confidence of these detections have been very low, because even though this plot shows many data points, most plots look like 1 point here, 1 point here, like 4 points in the entire plot, and the whole model plot, fitted along that. So there are several missions planned in the future to deal with this kind of insufficiency. And the most significant of them is JWST, the James Webb Space Telescope. So here we can see the wavelength ranges that the different instruments on the James Webb Space Telescope offers. This is what we had using Hubble, and this whole other range is what James Webb will have. So if the James Webb launches in the near future, which it is supposed to, fingers crossed, we will have much better data on the other wavelength regions and much better constraints on the atmospheric properties of other exoplanets. Once we have that, we will be able to say what the exact composition of other exoplanets are in the habitable zone. And then using those compositions, we can say whether it will have a greenhouse effect, whether it will have life-giving molecules, whether it will have rain, stuff like that. But James Webb Space Telescope is still maybe a long way in the future. And a lot of proposals have been written with the James Webb in mind. And right now, a common theme in the exoplanet community is that James Webb is kind of a fairy tale. And many proposals begin with, instead of once upon a time, it begins with once JWST launches, we can do this or that. Right. So that was an overview of what the field of exoplanets hold right now, and without going into too much details. And I'll leave you with this plot of the habitable worlds, the artist's impression. And I'll take any questions if you have.
Thank you, Agnibha. If the audience has any question, you can please go ahead, unmute yourself.
How exactly is the starlight blocked to see planets in direct imaging? Like,
oh, that was using a ground-based telescope. They used a physical thing, physical shield, an opaque, I don't know, iron or something, piece of metal, to block the position where the star is supposed to be.
it's physical in.
Yeah.
If there are any more questions, you can either type it in the chat box or you can unmute yourself and ask it yourself.
Yeah, the disk is like a coronagraph.
Yeah, exactly.
Covering the
exactly.
sun.
Yes, yes.
Same thing is used for exoplanet too.
Yeah, that's where the inspiration was drawn from.
Yeah.
Okay, I don't think we'll have any other questions, so we can move on to our reviewers. Dr. Ananthakrishnan.
Yeah. Okay. Agnibha, yeah, good talk.
Thank
Yeah,
you, sir.
good job. We're getting into the business of exoplanet, which is it's in its infancy when I was retiring. You know, it was, do you know who is the first person who found an exoplanet? It is not an optical astronomer.
Yeah. About around X-ray star or neutron star, something like that. I don't remember the name. It was in 1991 or 2.
Yes, that was Wolfscan.
Yes.
Wolfscan, who used the Arecibo telescope to get on a pulsar. That's why you said neutron star.
Oh.
I think it is 1257 minus 17 or something. I've read it has 3 planets around the star, around the pulsar. But it was not exactly a star, it was a dead star. Okay,
Yeah.
so people attribute the whole thing to who is that mayor and the other guy?
Hello.
Yeah. Okay. You talked about the mass of the, I remember jotting down something, mass of a planet for spectroscopy.
Yes.
And you talked about the proportion of the mass of the planet versus its orbiting star. The Doppler shift doesn't exactly follow any mass. It follows the speed.
Yeah.
Okay,
The
so
speed.
so
is-
what you are referring to is an orbital period. Okay, now
The speed
orbital
is
period has
dependent.
some relation to the mass.
Yes, the speed is dependent on the mass of the. It's a two-body thing. So
Yeah, right. So I think it needs to be stressed that the dimming and the spectroscopy signals moving back and forth. That depends on the
speed.
period at which the planet is going around the star. Okay, and of course, then you can correlate it with the mass.
Okay.
All right, not the other way around.
Okay. Thank you.
Okay, yeah, I
keep that in
mean,
mind.
you can have a large mass like Jupiter. It takes several years to go around the sun. Okay, it's very slow. Okay, whereas Mercury is only so many days.
Yeah,
Much,
actually,
much
in that proportion, the orbital period is also a factor. I didn't
Yeah,
mention
yeah.
it in the.
Yeah, because that will again go back to Kepler's laws and all that.
Exactly.
Yeah. Okay. Now, transit you said is not the ideal way, but I think that is how most of the planets have been discovered, right?
By not ideal, I meant that even if there's a planet, you may miss it.
Yeah, of course, because it is the dimming depends upon how big is the surface area with respect to the overall surface area of the
I mean
star.
the orbital inclination of the transit
Yeah,
probability.
of course.
So
Yes,
it's
if it is not in your line of sight, then
exactly.
you cannot see that. Yes, but isn't it true that out of these 4,400 or so
most have been
exoplanets,
discovered. Yes.
mostly it is due to this method, right?
Right.
Okay, so it is worth mentioning that in passing that this is the case. Although this is not an ideal situation, but this is the case because we are not left with many alternatives. Okay. Yeah, so there is these are good things. Now, habitable planets, there are many. You're a science fiction aficionado, as I saw in your small abstract. So the question which even I have been asked many times when I give a talk on exoplanets. I used to give, and now I have stopped giving because I become a dadu. So it's not useful to give talks. So the question which is asked is, can we get there? Okay. The answer, of course, is no. Okay, because it is even the nearest star is some 24 trillion kilometers.
4 light years, something.
Yeah, 4 light years. So that means 6 trillion miles to each light year. So 24 trillion miles, which even if you send a spacecraft, the fastest spacecraft is going now is the Voyagers, Pioneer.
Voyager 2, yeah.
That will take the next 100 years, if at all, if it ever reaches the planet, ever reaches the star, nearest star. And most of these stars are 50 to 100 light years away from us, right? So, but you talked of Venus, and have you been following the phosphine controversy?
I have.
Yeah, can you say anything about it?
Well, there were suspected detections of phosphine in the atmosphere of Venus.
Yeah, right.
And then they suspected that since phosphene only has organic roots, maybe there's something there that's producing it, or some exotic chemistry that we don't know of. But then it was it died down, and it was probably disproved by some papers that it was an instrumental error or something instead of a real detection.
Yeah, the authors are still holding out.
Authors, yeah.
saying that no, they don't find anything wrong in their discovery or whatever. Okay, in their results. I think it was published in Science, if I remember correctly,
Yes,
a year ago or
during the pandemic. Yes.
during the pandemic, and it seems that it is a very small, minute quantity, and that can be described by other means, and the data also are not very your same problem. The
So maybe
data sampling.
there are 2 planned missions to Venus in the near future. Maybe they can find.
Yeah, maybe they can detect. Yeah. Yeah. And lastly, of course, you talked about the JWST. If that happens. Yeah. So I do hope that it will happen this year, end of this year, or early next year, or something like that. But your conjecture is valid because it is a huge, monstrous telescope, and it's not going to be easy. Incidentally, it has also what is called a finder telescope. Did you know that?
I didn't hear that.
See, when you have large telescopes,
optical
telescopes, for example, it is impossible because the telescope size is so large that if you derive a lambda by d, then it will be a fraction of an arc second.
Yes.
And the field of view will be very small.
Yes.
Okay. So you cannot target it against any place.
The viewfinder kind of thing. Okay.
Yeah. So you need a telescope, in addition, a small telescope, in addition to this.
Like the finder scope.
Yeah, finder scope.
Yeah.
Okay. So even this has a finder scope. Okay. A small telescopes attached to the main telescope. I don't remember the size of the head.
I didn't know that.
Yeah. So that is used for initially focusing on the big field, and then it will focus on the small one. Okay. So Hubble telescope, which has been recently refurbished, they hope that it was about to die. So they have found a way of resurrecting it. And they will hopefully keep using it for the next several years, overlapping JWST, because that is still the best telescope for optical wavelengths. Whereas JWST will be working on the
IR.
Yeah, IR wavelengths. So you will have an interesting time to work on this for your PhD.
Yeah, my PhD.
You will get all your massive data.
Thesis topic actually has JWST in the title. So
I see. Yeah. I hope you get data. Are there any co-investigators on JWST in the place where you are going?
Yeah. My supervisor is a co-I on a proposal.
Okay. So he will get some data. So you will have a good possibility of working on that.
Hopefully.
It's going to be very exciting for you for the next several years. So we will hope to hear from you after, say, 5 years as to what you managed to achieve.
Definitely.
Okay. And as you know, the expectation from JBNSTS scholars is very high. Okay. So we hope that some of you will fulfill that requirement. We sort of scrapped through. I don't think we really made it there. And this is like the Olympic title. So we hope some of you get a gold medal. All the best.
Thank you, sir.
Okay.
Thank you, Dr. Ananthakrishnan. We'll move on to our next reviewer, Agnibha, Dr. Panigrahi, if you may.
Hi, Agnibha.
Hi.
Yeah, so I am very far from the topic of your talk in terms of my own knowledge or expertise. In some ways that was good because your talk was more at the level of a survey talk and pretty much at an introductory level. So I personally enjoyed your talk a lot. I think it was very easy to follow, even without knowing anything in the area. So overall, I would say a very, very nice talk. I have just a couple of minor comments. The first is in a survey talk like this, where you're talking about methods that have existed, where you're not focusing on things that you have been doing. It's nice to add some historical context to these methods. So if you could say a little about how these techniques evolved, who were the people who came up with it, when they came about, what were the sort of immediate incentives for each method, that adds a little context to what you're talking about. So that's one suggestion. The other is when you're contrasting a bunch of different, or when you're presenting a bunch of different techniques for the same goal, it's also nice to sort of contrast between the techniques in terms of what are the situations, or in what situations are some of these techniques better than others. In some cases, there are techniques that are sort of futuristic, right? Maybe there are techniques that exist in theory that haven't been particularly successful yet, but one hopes that they would be successful in the future under certain other conditions. So these kinds of discussions where you talk about what the merits and demerits of the techniques are, which of them have been successful so far, which are the ones to look out for in the future. This discussion helps sort of anchor your talk and make it a little more interesting.
Okay.
So I'd say just these 2 points I felt could have made the talk a little more engaging, but otherwise it was very clear. I think the thing that was particularly good about the talk was its clarity. There was pretty much anybody with absolutely no background in your area would still not get lost, and that's a good that's a very creditable thing to do. So yeah, that's all, and all the best for your PhD. You're still very early in your journey, so hope you do well.
Thanks. That was great feedback. I actually had a historical perspective kind of slide, but then I removed it. I don't know why. And I'll keep in mind the other one, the pros and cons kind of thing, comparing different methods. That sounds very interesting. I hadn't thought of that. Thank you.
Thank you, Dr. Panigrahi. Thank you once again, Agnibha, for that lovely talk.